Okay, so main claim, like I was saying. Okay, so why are Spivak normal fibrations so important? Because they allow us to decide when a CW complex is a Poincare duality space. So, let's say let X be a finite CW complex. So then X is a P space if and only if X admits a Spivak normal fibration. Okay, so I'm going to have a lengthy discussion of the proof, but I'm not actually going to prove it. So one of these implications is fairly easy, and I will prove that, and the other one is extremely difficult. And I will refer you to Andrew's, not even Andrew's book that we're working from. I guess it's, what's the name of the paper? Algebraic Theory of Surgery 2? Yeah. So it uses spectral sequences, and it's quite hard. So I'll show you how far we can get in that direction without having to start using that heavy machinery. So I guess proof discussion. Okay, so the first question is, what can we construct without using either one of these hypotheses? Okay, so X is homotopic to finite simplicial complex. Okay, so this is the simplicial approximation theorem. So any finite simplicial complex can be embedded in R to the n plus k for large K. So this is the simplicial complex version of the Whitney embedding theorem. Okay. So I'm not going to talk about K anymore. I'm just going to say, without loss of generality, we've embedded X into this large Euclidean space. So let's say X is embedded, so without loss of generality, X is embedded into this space. Okay, so take a regular neighborhood. So this hopefully will seem very familiar now we've done this Pontryagin-Thom. So take a regular neighborhood of X with this boundary. And I'm going to denote the inclusion of X into the regular neighborhood by I. And I'm going to note this induces isomorphisms. So I star and I upper star are isomorphisms. Because X is a strong deformation retract of the neighborhood. Okay. Oh yeah, I will also say, so we're going to call, so this is going to be our fundamental class for this neighborhood, this pair, I guess. So that should live in H, where are we? M plus K. Slow there. Boundary NX. Okay, so I could say twisted, although this is a neighborhood of Euclidean space, so it's definitely oriented or orientable. so I'm not going to twist the coefficients like I normally would with a fundamental class. And in fact, this is one of the assumptions I'm going to make for personal safety reasons. So remark, I'm going to assume everything is oriented now. Everything is orientable. So that's to say that the homomorphism of the orientation character is trivial, I guess, in the case of CW complex. I think I'm also going to assume everything simply connected. So this all works through in the non-simply connected case, but you have to keep track of everything, and I think it might be more a better explanation if I don't. Okay, so then I'm going to draw the following commutative diagram. Okay, so let U be any class in where should it live? There we go. So again, like with twisted coefficients, if I was using that. So this is going to be sort of our tentative Tom class, right? We don't know such a thing exists yet because we haven't taken a Spivak normal fibration, but let's see what information we can get out before we even use the hypotheses. Okay, so then the following commutes. Okay, so we've got the cohomology of X, and there's a map from that to the cohomology of this regular neighborhood. So this map is going to be given by cupping with, so I guess I need to, this is why I mentioned that these were isomorphisms, because I want to take the inverses. So that's where the variable goes. So this is going to be, so this is sort of looking a bit like Tom isomorphism. And this one is the one I want to look a bit like Poincare duality. So this is isomorphic by I star to H star of nx. This maps into here. So this is genuine Poincare duality. So I want to cap with this class here. So I guess phi is defined so that this commutes. So what does that make phi? So that makes phi of v. So going around the circle, I should have u. Actually, I'm not going to do that. I think I've simplified it in my notes, so I'm just going to write that out for fear of getting this wrong. Okay, so it should be v cap with inverse of u nx. So I think, so if you work around the diagram and follow like some commuting rules, sort of passing this and changing the push forward to a pullback, then this tells you it commutes. So this map is capping with some class, right? So that looks an awful lot like a Poincare duality relation because it goes from there to there. This is cupping with some class u, so this is like a Tom isomorphism. So in fact, right off the bat, so let's prove implies. Okay, so we're assuming, oh no, the other way, is implied by. So if we've got a Spivak normal fibration, then we've got a Tom class. So let's set U to be equal to that Tom class. So let's say Tom class. Is there a black in my nose? Okay, so as we know that phi is an isomorphism, okay, so that makes this an isomorphism, and this is an isomorphism, and so is this, which makes phi an isomorphism. Okay, so this gives us that phi is an isomorphism. So this gives us a unique class such that capping with something is an isomorphism. This is a definition of Poincare complex. So phi is an iso, which implies the operation is an iso. So let's say that goes from so where we've defined this to be this object. -1 U, so this is big U, cap nx. So Spivak normal fibration quite clearly has Poincare duality, has the base space of Poincare duality. Okay, so what about the converse? Okay, so this is the hard part. So converse. Okay, so we want to, so what have we got? So we've got x defined by the Poincare duality relation. We want to say this, okay, so this uniquely defines a U, I claim. So this is an isomorphism which makes, is it an isomorphism? I'm trying to say that now I've defined, so now that I've got an x, this uniquely defines a class U. So that commutes, yeah.
Because a priori you don't know, you don't know phi is going to be given by capping with x, but you can define U such that it commutes and say that is the map phi.
Yeah, okay, yeah. Okay, so I define U so that this map phi is capping with x. Okay, yeah, and that uniquely defines U up to sine, I guess. So that should give me a candidate for a Tom class. So x exists, and if we, I guess, set phi to be the Poincare duality map, so that this commutes, this uniquely defines U. To sine defines, actually maybe it's not even to sine, that doesn't matter, defines U. So this is some class, so this is our tentative Tom class.